Hello, I'd like to welcome everyone to the Organic Grass-Fed Dairy Research Roundup, which is the second webinar in our series about organic grass-fed dairy production in 2022. I'm your host, Alice Formiga of eOrganic, and before we begin, I just wanted to let you know that we have many articles and recorded webinars on organic dairy farming and research on our website at eorganic.org and on our YouTube channel. Today, I'm very pleased to introduce our two presenters. First, we'll hear from Dr. Kleves Almeida, who is a postdoctoral research associate at the University of New Hampshire. He will be discussing the carbon footprint of grass-fed dairy production using a tool called the Integrated Farm System Model. After that, we'll hear from Miriam Snider, who is a PhD candidate at the University of Vermont. She will be discussing the impacts of commonly utilized forages on rumen fermentation, animal energetics, and methane production. So with that, I am going to pass over the screen to our first presenter, Kleves Almeida. So I just stopped sharing, and Kleves, you can share your screen.
All right, thank you so much for the introduction. Hello, everyone, and it's a pleasure to be here today and talk a little bit about carbon footprint of organic grass-fed dairies using the integrated farm system model. So I want to kick off the webinar showing a brief outline of the presentation with the topics I will be covering today. First, I will talk about the importance of modeling for predicting greenhouse gas emissions. I will also emphasize how nutrient cycling affects the gas emissions. Afterwards, I'm going to show a brief description of the integrated farm system model, the IFSM. And I'm going to show also an example of a study that used the IFSM, and also simulations scenarios that are directly related with organic grass-fed dairies. And lastly, I will say I will give some take-home messages and open for questions. The importance of modeling for predicting greenhouse gas emissions. In the last decades, there have been several discussions worldwide concerning greenhouse gas emissions and its environmental impacts. And these impacts are related to many activities, and one of them is the livestock, which is have been considered one of the contributors for the greenhouse gas effect. And it's basically the accumulation of gases in the atmosphere that traps the heat that was supposed to be reflected off after the absorption of the heat that is necessary for the Earth's warming. So first, for those who doesn't know, that the biggest challenge we have here is how to guarantee food security and reduce greenhouse gas emissions at the same time. So food security means having at all times both physical, economic access to dietary needs for a productive and healthy life. And the question is how to increase the food production and the profitability of our farm systems in the same area. So I would say that feeding strategies and management are the most important approach we could use to achieve that. And models and programs are management strategies that could also provide a whole perspective of the farm and at low costs, and we can also have unlimited number of simulations depending on our goal and our focus in the type of production we're looking for. So about the global warming, this is a chart that shows the global average surface temperature in over 100 years, and the blue bars indicate cooler than average years, while red bars show a warmer than average years. So we can see that there is an increase in the temperature and over the past 100 years. And from these, all the many activities I'm gonna show across the presentation that can contribute to the global warming, livestock contribute with about 15% of the total emissions. And comparing all the other activities, human activities, which is called anthropogenic emissions. For example, in the US, in the year of 2019, the agriculture sector comprises about 10% of the total emissions. So we can see that it's one of the sectors that less emitted greenhouse gas emissions compared to the other source. And according to the FAO 2013, the greenhouse gas emissions, specifically from livestock production, from these emissions, 40% comes from enteric methane production, which is basically burps and farts from cows, from animals, ruminants. And here is just to show that greenhouse gas emissions from livestock are considered emissions that comes from a natural cycle. And I'm going to provide some informations for you guys about how does this work and how does the cow produce this methane. So briefly, here's some graphics figures that shows how methane is produced, it's formed. So we know that cows are ruminant animals and they have one big stomach divided into in 4 compartments: rumen, reticulum, omasum, and abomasum. And because of the fermentation of the carbohydrates and mainly cellulose, which is basically happening in the rumen, and in order to produce the products that are generated to produce the milk, fat, and milk lactose, and which we call as volatile fatty acids, acetate, propionate, and butyrate. I'm not going to go very deep in these topics, but just to provide an outline to you guys and understand how the methane is produced. And they are basically produced as secondary products. We can see in the figure that there are 3 phases in the rumen: the gas phase, the liquid, and the solid. And between the gas phase, we have the methane production that comes from carbon dioxide and hydrogen, the metabolic hydrogen available within the rumen. So in a comparative of half-life, we have methane with 10 years of half-life, and there is a greenhouse warming potential of 28. And we have also nitrous oxide and carbon dioxide. But the difference is the methane and the carbon dioxide that comes from the methane produced by the ruminants, we call carbon dioxide biogenic, because it basically comes from animals and plant respiration. And we can say that all this methane come from a natural cycle, which is going to be broken down into CO2 in the atmosphere. And therefore, this CO2 that it comes specifically from methane is very different than the one that comes from cars, airplanes, industries, and which we call that comes from fossil fuels. And all these, all these interviews that people keep saying or talking about meatless Mondays or stuff like that, it's not very true, because we need to consider a whole perspective and how is the reality and how does the animals really produce and how they affect the greenhouse effect. So I keep saying that the carbon dioxide that comes from methane production after being broken down in the atmosphere from ruminants, they are part of a biogenic carbon cycle. So they are different. And the emissions come basically from plant respiration and during agriculture or grasslands or crops. And the grass takes up the CO2 that is from the air by photosynthesis. The cows, after that, gonna eat this grass, which is made of carbon, cellulose. And then during the ruminal fermentation, methane is gonna be produced and release it into the atmosphere. So there's a cycle and so on. There's a cycle where the methane is produced, but also broken down, and then by photosynthesis comes back to the plants, which is going to be eaten by the cows afterwards. So another source of greenhouse gas could be from the nitrogen loss, and a high protein diet provided to animals could produce a disbalance in the energy nitrogen availability in the rumen. And then this nitrogen that is in excess in the rumen has to be either metabolized or excreted. So it's related to the nitrogen losses, and because of the manure management could have an impact. So how does that work? So basically the nitrogen will be absorbed through the rumen wall, and then we go to the plasma or milk, and then could be also excreted during the from by feces or urinary nitrogen. And all this manure that compose the manure will go through the soil, and then after that to the water. And during the conversion from nitrate to ammonia, which is a natural reduction that happens in the water and soil, could many intermediates could be produced, and one of them is there is a high global warming potential, which is nitrous oxide, and then with that could have an increase in the global temperature. And how do I reduce these emissions from the animals? It's basically dairy management, diet balance, and precision feeding. So talking in a nutritional perspective, so all this could reduce the nitrogen loss in the environment, and with that we could, besides having animals more efficient, we could also reduce the environmental impact. So going through the management strategies and use of technologies that we could achieve a reduced methane emissions in our system, we have many research and educational tools like the integrated farm system model. And we could access the performance, economic aspects, and the environmental impact of farm systems in a whole perspective, because it integrates many physical and biological process on a farm. And the main goal is to have an optimized food production system with the greatest economic benefit and acceptable environmental impact. So the IFSM is a free tool, and you just need to make a simple registration on the website and download it, and you're gonna have a limited number of simulations you could do. So here's just a brief whole farm simulation perspective. We could have simulations related to dairy farms, beef cattle, or crop farms. And the farm systems, they are simulated over many years of weather, so you can select how many years of weather information you want on your simulation. And it's designed basically for long terms or strategic evaluations. And all those parameters you can see in the figure, they have to be input during the data input. and because of that, you could have a whole farm perspective. So here's just a screenshot of the software, the program. And basically we work with three files, data files. One is related to the farm characteristics, one is machinery, and the other is weather parameters. And about the machinery and weather parameters, there is a IFSM default files, so you could use those default files, and you're gonna work only the farm characteristics, and these farm characteristics are related to the size of the area, soil characteristics, equipments and structures, number of animals, production, all those parameters that we do know when we have a farm production system. And as I said, it could be related to dairy or beef. It depends with what you're working on. So the modeling begins by inputting the data, the information we got from surveys. So here's why it's important. We answer the survey, so we gather all the information that comes from surveys or data sets. And after that, we're gonna do all the data input, and be able to run the simulation. So here, this last screenshot shows that we select the model output and the reports we wanna look at. So it's up to us. We're gonna select different tables and different parameters that we're gonna select. There are different types, 4 different types of tables, and we can just custom and select these parameters we consider essentials for our simulation. So I just brought for you guys also an study, an important study using the IFSM. And I believe that it's important to show how feasible is using this program. And this is a study from Dr. Cabrera lab at the University of Wisconsin. And he compared the different production systems. And here we can see briefly that they had these comparisons between conventional, organic, and grazing farm. And on the organic and conventional farm, in some cases, the reduction in greenhouse gas emissions may be achieved while maintaining or even improving profitability. So as I said, field strategies and all other activities that could improve profitability at the end of the day that's what is gonna be important to reduce the environmental impact and methane emissions. So we can see that in the second figure, actually figure 4, that there was less manure storage in the animals grazing, under grazing and organic farming, basically because we know that animals in those production systems, they spend more time outdoors. So there's a less production of manure in the house facility as well, and manure storage. So with those categories reduced, at the end, the greenhouse gas emissions, which here is measured by kilo of carbon dioxide equivalent per cow per day, was reduced. So I gathered some information from a survey was a study developed with the University of Vermont. Miriam Snider is our next presenter. So and Dr. Heather Darby, and they had this survey that was, if I'm not wrong, it was applied on 2019. And again, gather information from surveys and data sets with the farming metrics, indices, and are extremely important to create accurate simulations and represent real farm conditions. So here I used it for 49 milking cows, producing 9,305 pounds of milk per cow per year. And according to this survey, the most part of the herds, they were crossbred, and the average grazing area was 220 acres. So in the first simulation, we can see here a comparison of the average farm I gathered from the survey and compared to low grazing area and high grazing area. And we can see that according to low grazing area, we had less anthropogenic emissions, basically because there is less activities towards the land management. And then in the third simulation with a higher grazing area, we could see that there was also a reduction because there was less land emissions, and because of the higher area, it was a better net biogenic production. So in the second scenario, I compared the same farm with different legume-grass mixtures, and we can see that the third farm, there was no big difference between the first and the second simulation, but we can see that there was a decreased carbon footprint in the third simulation, because at the end, more dietary nitrogen, more excretion of nitrogen, there will be with that a less impact and the land emissions, and produce more carbon footprint. And here, the third scenario was comparing breed, and we can see that there was a reduction of carbon footprint in Jersey cows compared to Holstein, because we do know that Jersey produce more milk solids, and we have greater fat concentration, and that's why they are considered more efficient animals. And also because they're smaller than Holsteins, consequently they eat less and produce less manure. To finish the presentation then, I just have take-home messages. So farm metrics and surveys are the key factors for modeling, and the IFSM is a useful tool to complement farm planning efforts in order to explore innovative farming systems aimed to reduce energy nutrient loss. So further research is needed to develop sustainable strategies to reduce methane production in organic grass-fed dairies. We do know that some people are already using kelp and seaweed as dietary strategies, but we do have this necessity for more studies. And there is also a need for software programs specifically for organic dairy farming. Once these conventional programs we have, they are more related to conventional farms. With that, I would like to thank you everyone for the attention, and I will be happy to answer any questions you might have. Thank you.
All right. Well, thank you everyone for being here today. And I really just wanted to give you a brief run through of some of the things we've done this past year. And one of the major projects that we conducted and just got results back on was a continuous culture project where we looked at the impact of pasture composition and forage energetics on a grass-fed organic dairy production, basically using an in vitro model. So I'll give you a brief overview. We'll go through some of the survey results from the survey that Kleves just alluded to, and I'll run you through some of the methodology and pertinent results from this study. And then at the end, we'll put it all together, and then I'll take questions. So I'm sure a lot of you are aware, but just to give some background information, if you're not, we know that organic dairies and organic dairy production systems are a lot different from your typical confinement systems. For one, organic dairies, typically they have the NOP pasture rule where they have to have 30%, at least 30% dry matter intake from pasture. They can have organic grains and conserved forages, and they can have vitamins and minerals. And as you all know, an organic dairy doesn't have is not allowed to have like pesticides, synthetic fertilizers, antibiotics, things like that. However, when you're converting to this grass-fed situation, it's a little bit more stringent based on certain certifications. Grass-fed has to, they have to be on pasture for at least 150 days with 60% dry matter intake. And I say no grains are allowed. Certain ones are at certain stages of development, but we won't go beyond the scope of what's here. So I'll just say no grains for now. And we know that quite a few of our pasture-based producers are now becoming certified organic and certified grass-fed, and they're beginning to make the switch. And there's a few reasons for this switch, although they are complex. We know that producing animals on forage is cheaper because forages can be, depending on circumstances, a cheap, abundant feed source. And this can lead to an improved pay price. There are these perceptions that there's improved animal health as well as better quality of life for animals and producers. A lot of these perceptions that have allowed for producers to make the switch are based on their management decisions. But up until recently, there wasn't a whole lot of information known about why producers were making the switch they did and what influenced their management decisions. So these are some of the results from the study that Kleves was talking about previously. In this study, we asked grass-fed producers from around the country to talk to us about what they felt they were satisfied with their pasture qualities and about knowledge on their forage parameters, things like that. So this is a table showing the self-reported producer satisfaction of said pasture qualities, whether that be pasture quality and yield, stored forage quality, soil fertility and health, or stored forage yield. And it's ranked. We asked the producers to rank themselves from very unsatisfied with their pasture qualities to very satisfied. And I've highlighted the somewhat satisfied, satisfied, and very satisfied categories to give you an idea of who's happy and who's not, basically. And the category that says at least somewhat satisfied is a summation of somewhat satisfied through very satisfied. And what we were able to figure out, we found that the majority of survey producers, they were at least somewhat satisfied with their pasture qualities. I mean, just looking at the data, we can tell that there's some happy producers out there. Those that reported that they were satisfied also indicated they had greater milk production. This is from the same study where we were looking at, and we asked producers to tell us about their knowledge on forage parameters, like what do you know about growing high energy forages? What do you know about improving your forage quality? Do you understand your forage test results? How do you maximize your forage DMI and your energy requirements for cows? And we asked them to rank their knowledge from very low knowledge to very high knowledge. And I've highlighted two particular parameters in red: growing high energy forages and energy requirements for cows. So on average, our producers seem to indicate they knew quite a bit about growing high energy forages as well as energy requirements for cows. However, we saw about a 10% disconnect. We saw 83% of producers saying that they knew how to grow high energy forages, but then we saw 93% that said they knew quite a bit about energy requirements for cows. So we're kind of seeing this knowledge disconnect. Producers that we survey, they seem like they know quite a bit about energetics, both forage-wise and animal-wise, but maybe they're not getting the results they want based on pasture quality and yield satisfaction. So there's a possibility that maybe they don't know quite as much about one area as they think they do, or vice versa. So that does beg the question, how are producers meeting their animal energy demands adequately? How can we help producers grow forages to help meet animal energy demands? And what forages should producers utilize in their pastures? And is there a silver bullet forage out there? Which I can tell you right now, there's not a silver bullet forage out there, but we can try to at least find a forage that meets a lot of needs of our grass-fed producers. So to answer some of these questions, or at least kind of to bridge that knowledge gap, we started developing research questions about what is actually available in a typical pasture and how we can best utilize what's available. So we know that pastures are typically composed of a diverse number of forages. That's including legumes like clover, alfalfa, and birchwood trefoil. There may be some grasses in there like we like to utilize, or we're starting to utilize some warm season grasses like sorghum Sudan grass and millet. And then there's also things some forbs like chicory, and maybe some unwanted things like bed straw. And because there's this diverse number of forages and plants, there's this potential for there to be a diverse amount of plant and secondary metabolites. Metabolites obviously aren't the whole story, and our research didn't focus on that, but we know that diverse pastures are going to have a diverse energetic content, things like variable protein and water-soluble carbohydrates. So we focused more on the nutritional side instead of like this quote-unquote anti-nutritional factors like secondary metabolites. So we know that the impact of diverse forage mixtures on dairy nutrition and rumen performance hasn't been really well characterized. And the studies that are available, they're primary ecologically based, and they've been conducted in small plots. And there are a few animal studies, but they have provided mixed results. So we kind of attempted to bridge that gap using an in vitro model. The objective of this study was to evaluate rumen energetics and performance metrics. And we used diets that increased our cool season grass species with a steady supply of red clover. And then we conducted this in an in vitro continuous culture fermenter system, which I'll discuss a little bit more as we go along. We had 5 forages of interest. Our first one we looked at was orchard grass, and we utilized it. Well, it's really common here in the Northeast. It's high yielding. It has a pretty good sugar content, and it's pretty common as a hay grass, and it's good for pasture, and it grows back pretty decently. We also utilize red clover. You know, it's your typical pasture legume, and it's also commonly used for hay. It's high in crude protein, maybe not as much as some alfalfa varieties, but it's a good choice if you want higher crude protein. And it has high levels of digestible protein. Another good thing about red clover is it does contain a metalloenzyme called polyphenol oxidase, or PPO, which it's involved in the browning process in hay, but it may be useful in ruminant diets because it may have a protective effect against proteins and allowing for slower protein digestion. We were also interested in meadow fescue. It's not quite as popular as its tall fescue counterpart, but it performs really well in wet soils and drought, and it's actually more palatable, I think, than tall fescue. And it's a pretty good hay and silage type of forage. It does have superior NBF digestibility as compared to tall fescue, and it can also hybridize with perennial ryegrass, which I'll talk about in a second. Our fourth forage was Kentucky bluegrass. It tolerates close and frequent grazing. It's pretty palatable, more digestible energy per pound, and it also has high crude protein. And then finally, we've seen a lot of interest in the ryegrasses here in the Northeast, so we included perennial ryegrass in these diets. It's typically used for like hay and grazing situation, and we've seen it a lot in management intensive grazing operations. It does rapidly establish, which is why it's good for some of these more intensive operations, especially because it grows rather quickly. And it has a superior water-soluble carbohydrate content, which I'll talk a little bit more about here in a second. So this is just to give you kind of a window into our harvest and processing. We grew these forages, like the 5 I just discussed, as monocultures, and they were part of plots from other sub-experiments up on a farm up near the Canadian border. And we harvested these about 2, depending on the forage, 2 to 3 times in the morning. And then I would weigh them out, separate them out, weigh them out, put them in these bags, and try my best to get rid of all the air, because it was an hour-and-a-half drive to take it to a commercial warehouse where we store them for like negative 20 degrees Celsius. So after that harvest and a trip down to the warehouse, I would go and grab a bag, and then I would remove all the dead material and weeds and really weird botanical stuff from them before I'd flash freeze the forages using liquid nitrogen and dry ice. And we'd grind them through this Wiley mill here at a 2-mill grind. And then we would separate these out into their individual dietary components before I calculated what needed to go in what diet. So kind of moving away from the forage side and looking at the benchtop side, for this project, we collected about per period 20 liters of rumen fluid from 3 ruminally cannulated Holsteins. If you're unfamiliar with the cannula, it's basically a surgically created portal on the left side of the cow, because that's where the rumen is, so we could access rumen contents. And you have a pretty good view here of that solid layer that Kleves was talking about in his presentation. And so we would collect from this solid mass, we'd squeeze it and collect fluid, and we'd strain the contents into buckets that we kept warm, like at 39 degrees Celsius, and we'd bring it back to the lab where we would inoculate these vessels or the continuous culture fermenters with all of the fluid. So this fermenter, it's not technically, of course, you can think of it like an artificial rumen. Of course, it doesn't have all of the compartments or exact metabolism that's going on as the rumen, but we did our best to make sure that it was a pretty similar environment. And I'll just walk you through a little bit about it. So letter A, that's your agitator. It agitated at 70 RPM every minute, well, continuously, and then every 10 minutes it upcycled to 200 RPM. So it could stratify all of the stuff that would collect at the top. So this is kind of similar in the way to the rumen, where the liquid layer is at the bottom and the feed layer is at the top. So we have to stratify it and mix it kind of like ruminal contractions. This is our control tower. It has, it controls our pH, temperature, agitation, buffer, input, and outflow. I guess I can't say it really controls the pH, but it records our pH, because in this system, we do not record the pH to try to make it as natural a system as possible. This is the condenser. It controls cooling, and also because the rumen is an anaerobic environment, we would pump carbon dioxide in to try to maintain that anaerobic environment. Letter D, that's our pH probe. It's indwelling, and we collected pH every single minute for the entire 10-day period. And E is our feed port. So we would feed 4 times a day, and that's where we collected our methane on the last few days of our study. F is our vessel that held the rumen fluid. It can hold up to 6 liters, but because of the outflow spout, we can only fill it reasonably with 3 liters. And then we have a heat jacket controlled by the control tower. Keeps things at a constant 39 degrees Celsius, like the rumen of the cow. And we have buffer that would mimic the saliva. And then this was a dual flow as compared to a single flow fermenter. So we had 2 filters that would pump fluid in and out. And then we had a gravity fed spout that we could collect things in a carboy on ice from. So this big diagram, you don't really need to worry too much about it, but it's basically how we designed our study. It was to ensure that each fermenter received a diet at least once during the 4 periods that we conducted this study. And each fermenter received 110 grams of feed on a dry matter basis. Every single diet, all 4 diets, contained 40% red clover. The first diet contained that plus 60% orchard grass. The second diet, 30% orchard grass and 30% meadow fescue. The third diet, 20% orchard grass, 20% meadow fescue, and 20% Kentucky bluegrass. And the fourth diet was all 15% of the previously described grasses plus perennial ryegrass. And then I mentioned earlier that we fed these 4 times a day, and that was to mimic grazing intake patterns. So for 33% of the dry matter was fed at 7 a.m. and 4 p.m., and then 17% fed at 8:20 a.m. and 5:20 p.m. We had a few parameters of interest. So we looked at rumen pH, obviously, because an increased pH, our pH increases as dietary forage increases. And we know that rumen pH has a relationship with your volatile fatty acids. Your VFAs, our main ones of interest are acetate, propionate, and butyrate, although we did collect for other ones like isovalerate. And VFAs are important because they're the primary energy source for the animal. And typically you see a 70% acetate, 20% propionate, and 10% butyrate ratio in a forage fed animal. We also looked at ammonia and microbial protein synthesis, because we know that microbial protein synthesis requires a balanced supply of amino acids, ammonia, and energy. But sometimes traditional forages don't always provide these components. We looked at water-soluble carbohydrates in the rumen effluent. We know that a high sugar concentration typically means a higher animal performance and improved milk yield and an increased amino acid flow. And increased water-soluble carbs may improve the animal energetic balance. We did collect data for digestibility and forage nutrient profiles. And we also collected data for proteomics, but that's beyond the scope of this talk, so maybe for another day. And we also collected data for methane, because we know that increased water-soluble carbohydrates usually mean a decrease in methane. And the ones I will be talking about today are room pH VFAs, the water-soluble carbs, digestibility, and methane. So I'm going to throw a few tables and numbers at you, but you don't need to focus on the tables themselves, just on the trends. And at the end, I'll reiterate these in a more user-friendly version. So we looked at the apparent digestibility of all of our treatments. So we, again, have that binary orchard grass red clover treatment, the tri mixture with meadow fescue, the 4 forage mixture with Kentucky bluegrass, and the 5 mixture with perennial ryegrass. And we looked, and these are on a dry matter percentage. We looked at dry matter digestibility, organic matter digestibility, NDF, and ADF digestibility. And throughout the study, we saw that the treatment with Kentucky bluegrass inclusions, whether that be KYBG or PRG, they had a greater apparent digestibility than the meadow fescue and orchard grass red clover mixtures. So the more complex the mixture, it appeared that the greater the digestibility. And although this doesn't necessarily hold true, I guess, for the ADF, considering the perennial ryegrass mixture and meadow fescue mixture were the same. But overall, the Kentucky bluegrass mixture was more digestible, followed by the perennial ryegrass mixture. So these are, again, another big table, but just focus on the trends. This is some of our volatile fatty acid data. We looked at our total VFAs and then some of our individual VFAs, as well as our acetate to propionate ratio and the acetate and butyrate to propionate ratio. And what we found was that the total VFAs for each treatment, they didn't differ between treatments, and it means the diets were probably providing the same amount of energy to the animal, but based on some of the individual VFAs, it may be different types of energy being provided. So, for example, we know that the Kentucky bluegrass treatment had a greater amount of acetate as compared to the meadow fescue diet, although it technically is the same as the perennial ryegrass treatment. So what that indicates is that the Kentucky bluegrass treatment, it may be more prone to methane production because higher acetate usually is indicative of greater methane production, which we'll get to those results here in a second. Propionate, it was kind of to be expected based on what we saw at the acetate. The less complex mixtures like the orchard grass, red clover, and meadow fescue, they produce more propionate, which is more utilized for like the gluconeogenic pathway as compared to what's being used. So Kentucky bluegrass and the perennial ryegrass produced less propionate. So they're probably producing more methane and not being as energetically efficient as compared to the two less complex mixtures. And then kind of a similar story for butyrate, although once again, the orchard grass and red clover produced the least amount of butyrate. And we averaged all these together, and they basically followed that 70-20-10 ratio I was talking about earlier regarding a forage-based VFA profile. So looking at the acetate and propionate ratio, typically we want to see a 3-to-1 ratio of, 3 acetate, 1 propionate. Our numbers were a little higher, but it's still on par basically with a forage-based diet and some of the literature we've seen. And the same can be said for the acetate and butyrate plus propionate. We're not entirely sure what's driving this up as high as it is, but it's about on par with some of the research we've seen. So I'm just including a slide with pH, and nothing's highlighted here, but just so you know, there was no differences between treatments regarding pH. The mean pH ranged from like 5.89, 5.9 to 6.0, which is about on par with a typical pH from a forage-based diet. This is the fermenter methane output. So we collected methane on days 7, 8, 9, and 10, the last few days of that 10-day trial. And we used a handheld probe. So the Kentucky bluegrass treatment, there, as you can see, there's quite a bit of variation, but at the same time, it vastly produced way more methane than the perennial ryegrass, meadow fescue, and orchard grass red clover treatments. Those three did not differ from one another, but the Kentucky bluegrass treatment really produced a lot of methane, and it may be related to that acetate, those acetate levels I was talking about, but it can also be related to the water-soluble carbohydrate content. So we did look at the water-soluble carbs from the rumen fluid, and kind of inversely related to that methane. So as the methane increased, the water-soluble carbohydrate content decreased in the Kentucky bluegrass treatment. It was even less so than our day zero treatment, which had no treatment. It was from a typical TMR-based diet. So putting it all together, we might be able to say that diets with Kentucky bluegrass are more digestible, whether that be talking about dry matter, organic matter, NDF, or ADF. But the treatments with perennial ryegrass, although they were less digestible than the Kentucky bluegrass treatment, they were still more digestible with the orchard grass, red clover, and meadow fescue treatments. Our pH didn't differ between treatments, and our methane output was greatest for the Kentucky bluegrass, but then we saw when we included perennial ryegrass with that treatment, that methane did decrease. And we know that water-soluble carbs were lowest for the Kentucky bluegrass, which could correspond to that increased methane output. And just speculating, you might want to consider including perennial ryegrass in a pasture system for that increased digestibility and decreased methane output. And that's not to say don't include Kentucky bluegrass at all in your system. It's still perfectly fine to include, but you might want to keep some of the factors like methane production and digestibility in mind. So with that, I will take any questions or comments.
So I know we had at least one question in the chat here, and this one was directed at Kleves. How can we increase the profitability for organic grass-fed animals since they can't be fed concentrate?
All right. Yeah, I did see that question. It's a very interesting question, and I'm pretty sure that someone out there have the same doubt. But yeah, I would say that we have two different management strategies. One could be related to the forage management, because we know that forage with high quality, they have better or greater digestibility in the rumen. So animals that consume these high quality forages, they produce less methane at the end of the day. So another approach would be genetic selection, because we do know that more efficient animals, they would produce less methane intensity, which is measured as gram per kilo of energy correct milk, once they're going to produce more milk. So making the math at the end of the day, animals with a higher efficient and higher production, they're gonna reduce the methane production, and with that we're gonna have also a higher profitability. So genetic selection and forage management would increase the profitability and at the same time reduce the environmental impact.
But I had a question as well, and this one's also for Kleves. I was wondering, is there any support available for those people who want to try using the integrated farm system model?
Yes, I think I mentioned during the presentation that is pretty simple and easy to access the integrated farm system model. Just go through the website. You can type that in Google, IFSM USDA. You're gonna find out that it's available. You just need to make a simple registration, and there is a manual and there's some tutorials, so you can access and learn and play with the IFSM, which is very interesting. And you, as I said, you have unlimited number of simulations you could do.
Okay, great. Let's see. This is for either of you. Is there a difference in efficiency between different breeds?
Yes, there is. It's believed that Jersey cows, they are more efficient than Holstein cows because of the fat content. We do know that Jersey, they produce more fat compared to Holstein. So as I said, at the end of the day, you need to make the math according to their production. You cannot measure methane just the production itself, like in grams, but you have to relate that with the production, milk production or dry matter intake, which is methane yield or methane intensity. This last measurement, it's related to the efficiency of the animals. So jerseys, because they eat less and they are smaller, their rumen is smaller than Holstein, they would produce less methane because of the size, and also because, as I said, at the end of the day, they produce more milk solids, and making the math, they're going to be animals that produce less methane.
Okay. Let's see. Okay, so here's someone trying to put all these pieces together. If we're trying to focus on reducing greenhouse gases from dairy farms and also move to more sustainable systems like grass only, does the data suggest that we should focus on custom forage mixes to meet all these goals?
Yes, if I understand the question, it's kind of related to the previous question about the feed concentrate. We do know that organic grass-fed dairies, we cannot feed any concentrate diets, any grain. They're basically just grass. And the management, as I said, the percentage of legume and grass will vary according to the production you have. And as I said, you need to find the best. It's not an easy recipe. You have to find a dairy nutritionist, and according to the region you are and the soil conditions, there is a whole perspective that we have to look at, and then we're gonna come up at the end of the day with the best legume and grass and the best balance you have for your pasture for to feed those animals. And as I said, you have to also look it up at the nutrient losses. If there is really high legume proportion on your pasture, there is a possibility that you're gonna lose some nutrient during the excretion of manure. And yeah, you have to look it up at the whole perspective system and find out if you are being sustainable or not.
This is kind of similar to what Kleves was saying. This isn't a one size fits all. Like I could tell you all day, like you should put this in your pasture, do that. But it really comes down to management and what works best for your system. So it needs to be customized to your needs and what your end goals and farm management is like.
Makes sense. Okay. Did you look at the comparison between grass-fed or organic systems and conventional feeding? Feel free.
I know for us that we have not necessarily looked at the differences, as compared to like conventional systems. There's some really good research out there looking at that. There's some, I think, out of UNH, it's a few years old, but they did look at like needs of conventional systems as compared to your organic systems. And this, we're just now kind of trying to get down to, we're just now getting into some of the grass-fed stuff as it compares to organic dairy.
Yes, there are some comparisons, and one of them is the one I showed during the presentation. And as I said, you need to look it up at the whole perspective. Conventional feeding, you know that in animals they're gonna be fed as total mixed ratio, so they basically stay inside the barn the most part of the day or 24/7, and with that they're gonna produce more methane towards the housing facility and manure. But if we talk about animals that they are outdoors, those animals they're gonna eat more grass and graze animals, and they're gonna produce more acetate, which is could produce methane with that. And we have to look it up at the whole perspective. Animals that receive concentrate diets, they produce more propionate, which it's a hydrogen sink, and could reduce methane. But as I said, it depends the production system you have and what's your goal. Do you want to produce and also consider the environmental impact? If so, you have to consider all the parameters you have on your production system.
Okay. How much can we mitigate methane output from cows by modifying what they eat in the field? Do we have to buy algae, because that seems like more costs when we have fields of forage?
I don't think you necessarily have to buy it. If you think it works in your system, I'd say go ahead and try it. But there's some really good research out there, again, that where some of these, which I wish I could touch more on. There's some of these forages that have quite a few metabolites. So like bird's foot trefoil, I know how hard it is to get it to grow in a pasture system, but it contains things like tannins, which can potentially help with methane mitigation. I'm not saying go out and reseed your field with bird's foot trefoil this summer, but there are some plants I think that you could grow, so you don't have to go get some of these supplements. But again, it's just what's right for your production system, what works best for you. It's going to be probably a little bit of trial and error to figure out, do I just need to use plants? Do I need to use supplements? Or is there kind of a sweet spot where I have to get a combination of both?
So I would like to thank everyone who asked the questions, and thank you, Kleves and Miriam, for giving this presentation today. And thanks to everyone for joining us.
Thank you very much.
Thank you.